up, and I can sit here in front.
I was like, no, I still have to finish school. But I know
Yeah, you're probably gonna stand more like this.
Look for his application.
Right?
He said he's going to be over there.
Right on the spot.
Whiskers moved under my foot.
That's terrifying.
You are.
Today, guys.
Look at us.
That's right.
Yeah, okay.
Yeah.
Yeah.
All right. Well,
I'm going to do what I want to do.
it'll load.
Like, oh,
We'll just keep bringing it. If we can get them on.
and like,
And, you know, you'd think that you're gonna do this.
and then I'll send you
but
his, I'll send you his email.
Not gonna do what?
you don't get to go first. He knows.
Well, I don't. Right here. Because I have everything figured out. But then I'll.
Maybe you want to avert your eyes.
Don't stop the screen sharing.
And it's okay, don't have
Stop that.
No, I need that.
Yeah.
But Dan, since
Not the best.
we're going to have to reset that up.
There's windows.
Just mess with it.
You probably don't have to get.
They should have signed one that
But yeah,
sets the rule on the first.
like I have to be hired, like I have to know again.
No, it'll be fine. Never mind.
You said it didn't pay well, and I was like, you don't understand.
Yeah.
I was like, I'm not gonna tell you how much you make, because it might like affect our hiring quite legitimately.
Yeah. The second part, which is at 12:30.
Was,
Which is
Oh, that's awesome.
right here. Testing one across.
That's fantastic.
Yeah, so it's like both.
let's see.
It's only 1350.
So we're going smoothly for you.
But it's a 1385. So it's 3 hours. This
So you don't know if live streaming is working?
I'm going to know any minute now.
Okay.
It's outputting. The only thing I'm worried about is capturing the screen, but I think it's set up good.
Based on what baby.
Oh.
Sometimes it's better to do it. And there's one day.
Do you know what orange juice this morning?
Some minute.
Let's get down.
Oh, stupid.
Are you scared? I was gonna move your stuff, yeah. He's trying to figure out if the person.
Yeah, that's fine.
Someone said they can already hear us.
Dan, is this already more people than you expected? Yeah.
Stephanie's the meanest person in our office.
Yeah, she's the worst. It's because she's so beautiful. I wonder that'd be a point.
Well, like I say, we have to.
Christine does. That's what Christine does. Yeah.
It works for her though. That's why I'm so nice to you.
You're not nice to anybody.
No, she's a good spirit of me.
That's where we-
Okay.
It's my kind of thing.
She's a tease. I like it.
Yeah, you were brought up earlier.
So John says he's on Skype now, and he's asking if he should be watching the YouTube link.
It should be populating in 5 minutes. It will be starting up.
Okay. He says he hears voices.
Thank you for coming.
No.
It's really bummed that I missed yours last week.
Yeah, I think on your.
Doing the jail week.
I got to stop Rocco's jail oven, and then
I was in the bed.
you even have an orange one. I have no idea.
And hope no one is either excited or embarrassed by you. Hope you.
Right.
It's in a tub.
Like with the pokey belly guy.
I don't know about this thing because I have a dozen. Oh, I'm so excited about the cupcakes this evening.
Oh, I should write that. 6:30 is what I said?
7:30, I think. Let me double check. I'll look right now.
Well, I got myself down to like
All I wanna do.
see. I bought it, and it's like
6:30, Jen.
She got herself one too, and it's
Thanks, Fred. Welcome. Good to see you.
Trust me, out of everyone in this room, I'm scared of her the most.
Okay. What do you think? Are things working?
I think so. I'm gonna know in 2 minutes 40 because I have it scheduled to automatically start.
Okay.
So I know it's a waiting. Yeah, because this part.
Because your backup. What's that?
Yeah, my backup is to just. You can look and see what I have. So I basically have 2 windows. This window is for, you can't see anything on it here, but once I pop this up, it takes a shot of this.
Okay.
Then this is this guy, and so this is probably where the sound's at.
And then you'll repeat it. Can I squeeze behind you?
Hi there.
Good to see you.
Likewise.
Yeah, I heard your signature today. It wouldn't be class your body, but never give me anything like but now.
yeah, every meeting I bring it up. So finally he's like, okay, now I work on this. He's gonna send it out. Almost like it first. Okay. So yeah, that's kind of what happened. Right.
Or the dog man. How's that going?
I remember
All these people, Dan. Okay, what's going on?
I'm going to get started while we have people come in because it's rare that you get these opportunities to both talk about the wonderful things your students have done and potentially embarrass them at the same time in a public audience. So I'm going to have a shot at this. And so I first want to start out and thank two people that brought the system and these ideas sort of to us. So that's John. Talk about the wonderful things your students have done. And we'll make sure so everyone at the same time in a public audience see and hear us. So he'll call if he can't. So John came and gave a talk at Boise State and about the moose wolf system. And so he and I had breakfast together, and he sort of said, I think plants, yeah, they're probably important. I don't know what to do. And I said, I can help with that. As Chelsea calls it, the 4B lab special, right? Like, we can tell you what they feed on and why. And so at the end of that, John says, well, I have almost 2 decades worth of urine samples that have been archived. Would that be helpful? And I was like, stay calm, don't get too excited. This is very exciting. So having urine samples, right, tell you what the animal's been doing, right? So not only behaviorally, but also physiologically. So we have this archived of samples that went with the system. And so John and I, this was in 2013, he said, go ahead, come on in. Cool. He said, what did he say? Okay. He didn't say that he can't hear, so that's good. He said, well, why don't we start this project? He goes, I have crews that are going out in the wintertime, they're tracking moose, and we can collect urine and droppings and plant samples for you. Would that be useful? And I said, yeah. So we started doing this, and then we funded it sort of shoestring budget of cobbling together as much as we could. I had an undergraduate sort of get started on analyzing stuff, but we really needed a student. And so I thought I needed a very dedicated, sort of focused, diligent individual to take on this really important project. And so, where do you find someone like that? Somebody that looks like this. So if anybody's taken a course with Dan or seen him walking down the halls or wherever he is, this is the man I'm looking for this project, right? And so you may not know this about Dan. If you don't, you're not surprised. But he worked almost 12 years at a correctional facility. So this look comes in handy at a correctional facility. And so he knows how to manage people and how to get people to do what he wants them to do, right? I thought this is perfect. So now, how do you take a person that looks like this? Willing to work with someone like this, right? And so I had Dan in my lab, and he was very kind of scary, but I knew that he was up for the task, and I tried to recruit him. And I thought, well, I've got to convince him somehow that this is not too scary, that you can actually pull off something. And so what I realized is that the two of us share an interest. So he's enjoying the moose, the jackalope, right? So he and I both are very interested in thinking like herbivores think and trying to understand the mechanisms that explain their behaviors. And so because I had him in physiology, I knew that he was very interested in mechanism, and I thought this is the person that I should try and recruit. And I'll even say, so Dan's got a softer side, so I think actually in this picture that's associated in that. Interested in how sagebrush is responding to juniper removal. And I said, oh, hey, Dan, you want to do another project? He goes, sure, I'll do another project. And so he then worked with an undergraduate, Aaron Moore, and they looked at how cutting juniper increased phenolics in sagebrush over a short period of time, at least in low sagebrush and mountain elm. So he also worked on a very applied system. And then, like, he doesn't have anything else to do, so he applies for a grant that he gets through the Biomolecular Research Center to develop and test a hypothesis. I think in his mind he's won, but and then he tries all the rest of us. So he's incredibly competitive, which is great. He also is a good teacher. He can even teach old dogs new tricks. So Dan, you may not know this about him, but he does courses on dancing, right? So both swing dancing, different types. So maybe tonight, if you come to the celebration, Dan can teach you a few things. He's a dancer, that you didn't know. And then he also has taught my lab. So Dan was probably the only, not in a lab, not in captive studies, but out there in the world. And so he has been the background to helping me convince other systems and other people in other systems that think about predator-prey interactions to help them think about, well, maybe plants do play a role here. And so because of his data, I've been able to convince other people in other systems, all of these ones here, to take a chance at thinking about diet quality. So I have Dan to thank for all that effort. Okay, so now that's Dan's wonderful notice. And so he is going to now tell you about his thesis and
blinded by the thing or hiding behind the desk. So yeah, everything that Jen said, just bear in mind, if I mess this up, it's because I was overworked. So like Jen said, I did my research focused on filling in the disconnect between plant quality and population dynamics in herbivores. And for many years, dating back to the days of Aldo Leopold, researchers, managers, and just general wildlife enthusiasts have been interested in what governs population dynamics of herbivores. And they're faced with a lot outside of air-conditioned rooms or heated rooms to go hang out in when the weather turns bad. They're faced with external and internal parasites on a constant basis, regardless of season. Predation is a real thing. Quadrupeds and bipeds try to track them down all year long. They also have to face competition from their conspecifics for resources. All these things, they work together, and this poor little herbivore has got a major challenge to face. So most people, when they think of what governs these population dynamics, they focus here on predation. And that is largely due to all these wonderful Lockable-Terra models that show how prey populations and predator populations fluctuate in synchronicity over time. There's usually a lag. As prey increases, predator can increase later. As prey plummets, predator can plummet. And these models show very conclusive empirical evidence that predation does affect prey populations. But all plants contain some suite of secondary chemicals. All plants that grow wild contain some secondary compounds, these PSMs, which I will refer to as toxins from here on out, that has given rise over recent decades to this idea of bottom-up regulation. Herbivore populations being regulated by the food that they eat. And why not? I mean, plants are static, but they're not helpless. These are all camphor, campine, limonene, alpha-pinene. These are all toxins produced by most plants. Camphor, campine, limonene, alpha-pinene, they're produced in most conifers throughout the contiguous United States. This is a sagebrush that produces all these, but this guy, not made in sagebrush. It's camphor. And PSMs, these toxins, they're not created equal all the time. A stand of plants that grow together in a community can have different concentrations of toxins within each plant, and even a single plant can have different concentrations of toxins among its stems and leaves. So there's a lot of variation in these toxins. And this herbivores, they know this. They've developed ways to detect where these toxins are at and how to avoid them. And there's been a lot of research focused on herbivores and prey species that show they browse selectively with regard to these toxins. This is 2 projects that were conducted in our lab here at Boise State. Graham Fry worked on greater state concentration decreases and exponentially. So the birds are in some way detecting these toxins and nutrients and selecting what they eat based on that detection. This evidence has also been used in large. 2 of those phenolic compounds were positively associated with decreased browsing visits by moose. So they were being deterred from browsing again on these willow trees based on these 2 phenolic compounds that were increased following their first browsing visit. This has also been known to go all the way to starvation. Snowshoe hares, Norway rats to death, regardless of having food in front of them, simply because they didn't want to eat what was given to them, based on the toxin concentration within that food. The giant eland, which is the largest antelope in the world, also demonstrated the same tendency themselves for a while, and then they were forced to eat something good. So this has all given rise to this idea that in modern empirical ecology, herbivore populations are governed not only by top-down or bottom-up, but a combination of the 2. Quality work together to govern population dynamics of herbivores. This can be replicated, this equation. For those, is governed by what that population is eating and what is eating that population. So here we have B sub n is a conversion coefficient that shows what the food that they're eating, how much of that is being converted into new population members, minus what population members are leaving. The important part is this CV in the middle, which is the quality of food. Now, that's easier said than done. Based on these selection studies that were done, what we have is a disconnect between how the food affects the population dynamic, growth and decline. In order to understand this gap right here in the middle, you have to look at the behavior and physiology of the animal. In wild populations, that is difficult to do. And now this CV thing we're coming back to is all this mess right here. And how fun is that? Basically what that is saying is that food quality is not only a function of the plant toxins within the food, but it's also a function of the animal behavior. These two variables, they represent selection and encounter rate, basically what the animal is selecting and how much of it they're eating. The physiology and recruitment of the animal. So capital M represents the detoxification capabilities of that animal. And the relative health of the animal, represented by toxin content divided by detoxification capacity for that animal. All of this goes into explaining these two little variables, food quality. That's problematic in natural systems because you got to know what's being eaten. You got to know the toxin concentration of what's being eaten. You got to know how much these animals are eating, not only in terms of biomass, but also in terms of toxins that are being ingested. And you have to know their physiological capabilities for dealing with these toxins and whether or not these have nutritional effects. And if you can address that, which is what I'm trying to do, I'm looking at these two hard-to-do components for my thesis. We can get at an idea of whether or not the browsing is toxin-mediated and whether there are nutritional effects based on ingested toxins. This was the focus of my research right there. So to do this, went halfway across the country to this little tiny island right here in Lake Superior, IdahoWatch. Many of you in this room are very familiar with this system. For those of you who are not, IdahoWatch is a forested island in Lake Superior. It's 22 kilometers from the nearest landmass. It's 544 square kilometers. Balsam fir is a dominant form of vegetation, and it's famous for being a very, very, very well-studied predator-prey system. It is the only single predator, single prey system in North America, which makes it very accessible to researchers. These single predator, single prey systems are very rare. So when one is found, it is a fantastic for people to research population dynamics, predator and prey interactions. IdahoWatch consists of a single large prey species, the moose, which showed up in the early 1900s at some point. How they got there is subject to some debate. Early use of the island was for mine prospectors. So the popular theory is that they swam the 22 kilometers from the Canadian mainland to the island. That's a popular theory. Wolves showed up sometime later in the late 1940s in a particularly cold winter that froze Lake Superior solid. This pack of wolves migrated to the island. They found this bountiful supply of moose for them to prey on. Why leave? They had trees, they had food, they had cover. They had everything they wanted, so they stayed there. Then the ice melted, the lake turned into water again, and they were stuck. Thus was born the IdahoWatch predator-prey system, and over 53 years of continuous research, this Lacobotera model shows population dynamics of wolves in blue, moose in orange, and how they fluctuate. When wolf populations are high, moose populations are low. After the wolves crash, moose grow, wolves are still low, then the moose crash, and wolves start to gain again. This moose crash was caused by a severe starvation event in 1996, so there was a lot of carrion lying around for the wolves to scavenge on, which gave them a surplus of easily available food. So we know on the island, moose die from two things, predation and starvation. Now they are subjected to winter ticks every year on the island. Ticks themselves do not cause mortality, but they may play into some of these things by weakening the animal. But for every carcass that is found, it can be attributed to one of these two causes of mortality. This is the current Lacobotera model. I want to draw your attention to this end of it. Wolf numbers in the red, way down. Moose numbers are on the climb. For the last 2 years, there were 3 wolves and approximately 1,300 moose. This number is red because it's considered to be a low estimate because only 3/4 of the plots were actually sampled in that year. And in 2017, there were 2 moose remaining with approximately 2 wolves remaining, with approximately 1,600 moose on the island. Those 2 wolves are not breeding. There's no recruitment going on. So future projections with this idea that herbivore populations are governed by top-down and bottom-up controls is going away. As early as next year, there could be no more wolves on the island. So which means moose populations will be governed strictly by the food that they eat. And the food that they eat is this guy right here, balsam fir trees. Balsam fir trees, if you're not familiar with them, are the traditional Christmas tree. So now everyone has a frame of reference. So if you take nothing out of this talk, it's take away that moose eat Christmas. So the question is, how is this going to work? What's going to happen with the moose population? To answer these questions, I had two basic questions. One, do toxins influence dietary selection? And two, do toxins have an effect on nutritional condition? My objectives for the first question are to determine what are the moose eating, how much are they eating, not only in terms of biomass, but also toxins. Is their browsing toxin mediated, and what are the factors that influence how much they eat? The first question, what are they eating, that was done by someone else. So that one part was easy. This comes from Parikh et al. In 2016, where they measured all the available winter browse on the island. And over winter, there is on the eastern end a lot of balsam fir here in the dark gray. On the western end, there's some balsam fir, but there's more cedar. So basically their options are balsam fir, cedar, or deciduous twigs that have lost all their leaves. This right here, these two pie charts here represent what is being consumed. So what they did for this publication is they did microhistology on fecal pellets to determine the proportion of these that are being consumed. And as you can see, where balsam fir is big, it's also the main thing being consumed. No big surprise there. But the interesting thing here is on the west end, balsam fir is the second most abundant forage option, but the most abundant consumed option. So this confirms what all other publications say, is that balsam fir is a primary winter forage option for these moose. So now we know what they're eating, mostly. So now we have to find it on the island. So what we did is we found these moose tracks in the snow. They leave pretty definitive tracks. And we followed those tracks to a browsing patch. A browsing patch was an area where there were 3 or more balsam fir trees that were browsed on that were within reach of the moose with respect to the tracks in the snow. So basically they had to stand on those tracks and be able to reach the tree. So the length of their neck was how far from these trees, the tracks the trees could be. So approximately a meter, slightly less than a meter. Browsing marks are pretty easily identified. We'll get to that in just a second. What we did is did this for 3 years, 2013, 2014, and 2015 on both ends of the island, west and east ends. And these blown up pictures here represent that the circles are 2013, squares 14, triangles are 2015. And this is what a browse mark looks like. Moose is an Algonquin term, a little gee whiz info for you guys, that literally means twig eater. And the reason is because they eat the twig, not just the leaves like other herbivores do. So identifying browse marks is pretty easy to do. So now we know what they're eating. We got the plants identified. The question is, how much are they eating? That's where this comes into play. 1987, Reisenhower wrote his entire doctoral dissertation on finding ways to answer that question. And he was able to extrapolate an equation specific to the balsam fir on this island that shows rate of intake based on bite diameter. So the diameter of this twig can tell you how much they're eating in terms of intake rate, grams of dry matter per minute. He did a lot of field studies watching moose eat, and he came out with this equation that fits pretty well. So when we took our samples, we followed the moose tracks in the snow, found the browse samples. In order to know what the toxin concentration was, we measured that bite diameter with a pair of calipers to the nearest millimeter, and then we took a representative sample at the same bite diameter from the same tree. So balsam fir grows in these whorls right here, and it grows a new whorl each year. So it's really easy to age these trees. Now, remember what I said earlier about plants can have different concentrations of chemicals within a plant? So within balsam fir, each whorl being a new year can have different chemical concentrations each year. So we measured their bite diameter of the observed browse plants, and we took our relative sample from the same whorl on that tree. So that way, we're not, confusing this idea of interplant variation chemistry. We also looked for non-browse trees, trees that the moose could have eaten, had access to, but chose not to eat. And we took a representative sample from the non-browse tree at the same bite diameter from the same whorl. So browse and non-browse were grown in the same year. One was eaten, one was not. We took samples from 3 browse and 3 non-browse trees, and we shipped them back to the lab. This is kind of what they look like. Ground those all into a fine powder using liquid nitrogen and did a whole bunch of chemistry to them. We use gas chromatography to calculate total monoterpenes, colorimetric assays for total phenolics, radial diffusion assays for total tannins, and then we sent a bunch to Dairy One Laboratories in Ithaca, New York for total protein content. With all this data, we used a pair design using Akaki's information criterion with conditional logistic models, C-logit models, under a survival analysis with a binary response. What all that means is that if it was browse, it was determined to be killed. So it was given a 0. If it was unbrowsed, it was determined to still be alive, aka survived, it was given a 1. Binary response. And then we use the AIC tables of the C-logit models to determine what factors governed whether or not a plant was browsed or not. What we found was that camphene, a very common monoterpene found in pretty much every conifer that grows in the contiguous United States, was the chief governing source for browse selection. It emerged as the top model. The second model was bornyl acetate, another monoterpene, but it was greater than 3 delta AICs from the top model, so it was not considered a competing model. And this tells you what was the chief governing source, but it doesn't tell you direction. Right here we have this figure showing browse state on the x-axis, concentration of camphene on the y-axis, and we see the browse trees were higher in camphene than the unbrowsed trees. Ergo, the moose were selecting for camphene. The trees that they were eating had higher concentrations of camphene. Then we asked the question, what determines, is there a threshold at which they can detect this? So we used the generalized additive model. What this shows, this 0 line right here, is no selection. Anything below this line is things that are selected against. Anything above this line is things that are selected for. So we see at approximately 98 to 100 AUCs per milligram dry weight, the line goes up and moose are selecting for this compound at roughly 98 to 100 AUCs. Below that, the line below the selection line is flat, indicating there is no selection going on at lower concentrations. So this data indicates that moose are in some way detecting the camphene at these or higher concentrations and selecting it for their browse. This is counterintuitive to the idea that herbivores avoid PSMs, but in laboratory studies that were done, camphene was shown to be the least toxic of most monoterpenes that make up plant essential oils. And it was shown in a dose-dependent trial to have insulin production and liver damage properties beneficial to the herbivores. These are dose-dependent. In low doses, their insulin increases, liver damage decreases, animals all around healthier and happier, which may be important later on when we get to the detoxification. Also wanted to know what factors influence intake rate. In this analysis, we use generalized linear models to determine which factors, chemical or environmental, influence intake rate. We ended up with 3 competing models. Camphene emerged on top again, but snow depth and bornyl acetate emerged as competing models. Instead of doing a bunch of messy model averaging, I decided to look for interactive effects. And what I found was the interactive effect between camphene and snow depth emerged as the top model to determine intake rate. Second model was the null model, and it was still slightly greater than 2 deltas from the top model, but the top model explained everything better than anything else. So what that looks like, pictorially speaking, is coming back to one of these 3D figures. Here on the horizontal axis we have camphene and snow depth, and on the vertical axis our response variable, the bite diameter, aka intake rate. And we see that as snow depth increases, bite rate dramatically increases, which makes intuitive sense. The deeper the snow is, the less the animal wants to move around, the more it's likely going to stay in shelter and browse from the same trees. What's slightly less to conceive of is this idea that camphene, as it decreases in concentration, bite diameter increases. Now think back to bites on these selections that they're making. So for some reason, moose are selecting higher concentrations of camphene at a smaller bite rate. This is a gas chromatogram readout of browse and non-browse trees. This third peak right here, this is camphene. This little tiny peak right here is an unknown compound that despite our efforts we were unable to identify. These two compounds had a 97% correlation. It is possible that this compound exhibits some sort of acute toxicity. So while they want the caffeine, it comes with this little one in it that they don't want. So they take the smaller bites at the lower doses and just take more bites than taking the larger bites that maybe oversaturates this compound and makes them sick. It is also possible that the caffeine co-occurs with compounds that we do not individually measure. So we measure total phenolics, not individual phenolics. It is possible that caffeine co-occurs with some individual phenolics that we did not identify. So going back to questions that were asked, what we wanted to do, wanted to find what was being eaten, which we did. I wanted to get the toxin concentration, what was being eaten, which it did. And then the harder question is how much is being eaten. And thanks to Reisenhuber, we were able to do that not only in terms of biomass, but also in terms of toxin concentration. And we were able to get at this toxin-mediated browsing and say that yes, it is in fact toxin-mediated. That brings us to our second question. Do toxins have an effect on nutritional condition? Our objectives for this was to determine physiological effects of ingested plant toxins, nutritional condition of ingested plant toxins, and can this effect be tracked through time? Everybody intuitively knows that bad things you put in your body aren't supposed to be there. And in order to get rid of them, our body has to do something with them. So we have two phases of detoxification through our metabolic pathways. We have a phase one, which involves the additional function groups to whatever xenobiotic we just put in our body. This is done through cytochrome P450 enzymes. And then phase two is conjugation with some carrier molecule. There are a number of different conjugation pathways an animal can use. The one I was mostly concerned with was one known as glucuronic acid, which is a product of this enzyme, UDP glucuronal transferase. Basically, the way it works is when we ingest something bad, the liver plays matchmaker, and it takes the sugar and pairs it up with this enzyme, this UDP glucuronal transferase. When those two get together, they make sweet magic happen, and you get this molecule right here, UDP glucuronic acid. Most ingested monoterpenes and plant toxins are lipophilic, which is to say that they do not like water. They will absorb into tissues more than water. So what this molecule does is it bonds to these lipophilic toxins and makes them water soluble and shunts them to the kidneys so that they can be excreted. The way this works costs money. It costs energy. So this molecule right here is alpha-pinene. It is a very common monoterpene. When it is ingested, it must first be oxidized through the phase one pathway. This is CYP450 activity, so that requires ATP, so it requires energy. Once it's oxidized, it has to be conjugated to glucuronic acid through this conjugation pathway. That is a UDP-GT pathway, which is also ATP-driven, so that costs energy. Glucuronic acid itself is made directly out of a molecule of sugar. So if you think back to your cell biology days, one molecule of glucose is, I believe, 32 net gain ATP once it goes through the Krebs cycle and everything. So for every one of these molecules it's made, that's 32 ATP lost. So the ATP spent on making this stuff plus the loss of sugar itself, and you're left with a loss of endogenous energy reserves. Just to detoxify your food. This graph was taken from Cervello et al. In 2000, and it shows whitetail effect on glucuronidation than cedar and hemlock combined. So we expect in Iowa Oil, where they're eating primarily balsam fir in the winter, that they will have pretty high glucuronidation rates. The tricky part is, will they maintain an energy balance, positive energy balance? Think about this in terms of a savings account. When you take more out of your savings account than you're putting in, sooner or later your savings account is going to be empty. Energy balance is the exact same way. The more they eat of these toxins, the more energy they have to spend on detoxifying this food. If they spend more energy than they're getting out of the food, then they develop this negative energy balance, and their savings account is empty, and it's time to break out the credit card. So what happens when they break out the credit card? When mammals break down protein, they produce urea. Urea, they break the protein down into its amino acid constituents, and that is converted into urea and excreted in the urine, right? So if they have negative energy balance, they're in an energetic deficit. That deficit must be made up in order for them to maintain function. In order for them to get up in the morning and go find more food or run for predators or whatever they're facing, they have to make up that balance and get that energy from somewhere. They do this by catabolism of their own endogenous proteins, which is to say they essentially start to digest themselves. So under winter conditions where nutrition is restricted and they're not having healthy stuff to eat, they're catabolizing this endogenous proteins. This is going to lead to an increased production of urea in the excretion. So under winter conditions, this increased production of urea can be seen as an index of nutritional deficit. A number of research papers have been published on proving this in controlled feeding trials. This is the first, as far as I know, attempt to use it in a wild population. So what I predicted to see is that as GA to C increased, UN to C would increase in the urine, which is to say, as my index of toxicity increased, I would expect an increase in my index of nutritional condition based on the energy allocation required to detoxify that food. So the way I tested this, going back to these tracks of urine in the snow, as Jen said, for better than 20 years, I think it was 28 years, I'm thinking, urine samples were collected. Researchers in the snow, they came across where a moose had peed in the snow, they would scoop that up and put it in their pocket. They'd take it home, thaw it out in the lab, they put it in 2 different vials. One vial was sent to Wolf Laboratories in Minnesota for analysis for urinary nitrogen and creatinine. Creatinine is a compound produced through the breakdown of creatine phosphate in skeletal muscles. It's produced at a constant rate based on lean muscle mass. So for this application, it's a very useful tool for accounting for dilution from the snow or relative hydration of the animal. So everything's taken as a ratio to creatinine. The other vial was sent to me here at Boise State to quantify the glucuronic acid. I got 18 years of urine, of moose urine, in the mail one day. It was a magical day. I had approximately 40 samples per year. And I did this analysis on all of them. What I found was within a year, 2013, 14, and 15 are the 3 years for which we had browse data, which we collected samples from trees. Each one of these dots represents an individual moose that was tested. And I found positive correlations as predicted between my index of toxicity and my index of nutritional deficit. So we found positive correlations within years with individual animals. With that entire 18-year data set, I had 1 year that was contaminated, and so they had to be discarded. 17 years made this positive relationship. Each one of these dots represents the average per year. 40 moose per year tested. Each one of these dots is the average of that. And we still maintain this positive association between toxicity and nutritional deficit over winter. I want to draw your attention back to these Lacovotera models and how they have been very useful in tracking population dynamics between predator and prey. The same concept can be taken and used with urea and glucuronic acid. So this is my 17 years of samples spread out in Lacovotera fashion with GA to C on top and UN to C on the bottom. And as you can see, they track relatively close over time. And with this, we can take from a simple urine sample, we can take a single point metric to tell people the relative nutritional condition of an overwintering population, and by extension, the condition of the food that they're eating. Set out with 2 questions and a number of objectives. I wanted to know what the moose are eating, balsam fir. I wanted to know how much they're eating, bite diameter determines intake. I wanted to know if it was toxin-mediated browsing. Yes, they're preferring camping. I wanted to know the factors that influence intake rate, snow depth, and camping. I wanted to know the physiological effects. I found that it increased production of detox metabolites as increased toxins were ingested. I wanted to know effects on nutritional condition, which resulted in the loss of net energy reserves. And I wanted to know if this relationship could be tracked through time, which it can. So we've answered these 3 questions. Physiological and nutritional effects, check. We were able to get to that. The 2 hardest parts in a wild population, able to make that connection. And we were able to determine that there are, in fact, toxin-dependent nutritional effects in this wild population. This represents, as far as I know, the first study to make a direct connection between food quality and population dynamics when these 2 variables of behavior and physiology are considered within the population. These methods, they provide a simple, non-invasive, relatively inexpensive, time-efficient, and versatile collection of methods that can be used in any system on any herbivore, so long as appropriate experimental design is implemented. They have been tested on sage grouse and now the largest browsing ungulate in North America. All without the need for time-intensive and monotonous field observations and plant chemistry analysis. We can just go out in the field, pick up some excreta, put it in our pockets, go back to the lab, an afternoon of chemistry, and we have our answer. As Jen is fond of saying, the story is in the poop, or in this case, the pee. So with that, I'd like to thank my committee members, Dr. Jennifer Forby and Ian Robertson, who are in attendance today, Dr. John Busatich, who is tuning in remotely from Michigan Tech, support personnel, Dr. Leah Busatich, and John Henderson from Michigan Tech, who organized all the logistics for this, Laura Bond, our local statistician, who helped with all the AIC problems, my lab technicians, Mackenzie Hansen and Laura Heller, who, bless their souls, did hours of monotonous sample prep, and 4B Labbies past and present, especially special shout out to Chelsea Britt, who helped me with all the techie stuff that I'm not good at, and Chelsea for keeping me sane during 18 miserable days on that island last summer. And a special shout out to Brecken Robb, who is here today, fresh back from Ghana. She actually started this project. She did all the initial research that got this project going, without which I would not have a master's project to tell you about today. And with that, I'll take your questions. Right.
So, with Ian on your committee, I mean, what about, the added protein in twigs of insects and insect galls, insect eggs,
That's a
stuff
good
like that?
question.
I mean, you find that on the underside of blossom fruits, like insect eggs a lot.
I'm not familiar with insect galls and eggs in really, really cold winters. I don't know if they subsist through the winter that way or not. I can tell you that research has shown that ingested proteins do also affect urea output. However, the protein content in balsam fir alone, not accounting for insects, is not high enough to meet the minimal required needs of moose for metabolic properties. So that's the best answer I can give you. I don't know about how much the insect eggs add to it. Nuts. Great.
Oh,
Ouch.
Is balsam fir like a typical moose food thing?
Oil it is.
No, that's not the question. In general.
Moose do browse on conifers primarily, so you get away from Isle Royal, you have other contenders like Scots pine is also a favorite one.
Are they as toxic?
I have no idea.
Mm.
I don't know. The only other thing that browse on the island is cedar, which we did not do plant chemistry on cedar. However, going back to the Cervello paper, the balsam fir was more than double the GA output of the cedar. So with balsam fir, with that evidence published, and with balsam fir being the primary evidence, primary food item on the island, that's where we focused our
Yeah.
Yeah, great presentation, Dan. Thank you. It's kind of a side question is, what happens if the wolves do die off on this island? Is there talk about reintroducing wolves back to the island?
There is.
Yeah.
There is. So Isle Royal is under the control of the National Park Service, and I am no expert on Park Service politics, but the idea has been posed to reintroduce wolves, and there are proponents on both sides. There are people that say, yes, do it, keep the system going, and then there are people that say, don't do it. They got there naturally. Let nature take its course. So where the Park Service is currently at with this, I don't know. Last I heard was they had no plan to reintroduce. Amy?
I'm glad Roger brought up proteins. I have a question about protein. So you said you looked at protein content, but I didn't see it in any of your models or anything. I mean, did you find anything with they're selecting for or against higher or lower protein concentrations in the winter?
No.
No, you didn't find
No,
anything.
that was included in the models, but there was no selection.
So my question is, do you know what their protein intake might look like in the summer? Do you have any idea?
I have no idea.
Because in animals like moose, and elk, and caribou, and things that sort of are high altitude, well, actually all ruminants, but especially them, they have a lot of like physiological mechanisms to take in a lot of protein in the summer and then recycle that into the winter. So it's sort of, that's maybe why you didn't see as much of an effect. But I think there's also a lot of research that's been shown that summer nutrition affects, like has these really long lasting nutritional effects all the way through winter. And so if you had some sort of information about what they might be eating in the summer, it might give you a clue as to why you might be seeing like downstream nutritional deficits.
Right.
And it doesn't necessarily mean that their nutritional deficit is from what they're experiencing right now in winter, but it could be like a hangover effect from what they experienced 6 months earlier.
Right. I acknowledge and accept the importance of summer nutrition and how their ability to make it through winter is largely attributed to their nutritional quality of their summer and how they build up their fat reserves and their body reserves and everything. My study was focused primarily on winter browse options. And they're not going to not eat all winter long. So they're going to eat something, and that something is going to have an effect, theoretically. My study was focused on what they are eating and what effect it is having over winter.
Yeah, I think it was a really awesome presentation, excellent like method and mechanism. So I'm just curious if you have any way that you can think about that maybe the metric you use does sort of capture summer nutrition in a long sense way. That might be an interesting thing to sort of consider, because I think you can make the case that it might.
I think if we were able to get body mass metrics going
Yeah.
into winter, that would be helpful.
Yeah.
Our sample design was late January or late February or March, so right in the heart of winter, after they've supposedly burned through the majority of their summer reserves.
So, do you think this metric would work in, say, the West, where primary moose browse is deciduous? So, would there be enough change in phenolics to actually see a difference in the metric?
You talking plant phenolics?
Mm-hmm.
I think
And related to the area.
I think there would be. I haven't done any phenolic assays on any deciduous trees. I think it would be a lower concentration of almost all classes of toxins within the deciduous trees. And I think you would, just extrapolating what I've seen in my various laboratory trials, I think you would see a decrease in glucuronidation. However, I think you would see that change in winters like last winter, where we have a lot of snowfall. And we have variable interconnected habitats where the moose can go somewhere else. I think the reason why it works so well on the island is they can't go anywhere else. They're stuck there.
And they have very limited resources
Right.
as far as underground.
Right. But I think this metric is very pliable to our habitats here in terms of the urine use. So with field sampling techniques where we can identify that this urine that we're looking at came from a single animal and not a group of animals, then the same methods apply, the same principal methods apply. You can look at that and you can determine, based on the index of nutritional deficit, the relative health of your population that you're looking at.
Like you were making your research in a like kind of tiny little island. So I was wondering, that seems like a closed kind of system, and I was wondering, in matter of representativeness, which variables in other places of the world, or like we should have this kind of relationship between moves and what they eat and toxins, which variables do you think that will affect this behavior of the moves in other parts of the world?
Selectivity, I think, would be the most important variable. So you go, say, to Northern Europe, where moose are very prevalent and they eat primarily Scots. But they have connected habitats. They're not on this closed island. They can go from one habitat to another where maybe they have a different type of browse selection available. So I think the selection at that point would be the biggest variable, and probably their ability to move, to migrate. I mean, 544 square kilometers on an island doesn't give them a whole lot of room to move around.
Very nice presentation.
Thank you.
Do you think that you could predict migration patterns based on plant chemistry and with the same metric, like move it to migration instead of population numbers, like spatially?
I don't think so. I don't think you can get to migration. I think you can just get real-time point data that tells you what's going on right here, right now. Getting to migration would require tracking individual animals through a migratory route and taking samples along the way, which would be interesting to see. Jen?
So there's studies where people have done this with NDVI, right? Tracking movement of ungulates associated with green-up. And so why not do it with changes in toxins? And how might you do that?
By taking lots of plant samples and coming to your lab and saying, Jen, I need to borrow your stuff.
What's Berkeley doing?
That's exactly that.
Do you think you can remotely sense toxicity as well as you can green-up?
There's been, if memory serves, some ideas postulated that you can through spectroscopy. Maybe I'm wrong. Peggy!
How are they choosing the camping?
How? I
How?
have no idea. My theory is that they smell it somehow.
Okay.
Moose are typically considered to be wandering browsers, which means they eat on the go. I think that it's something that they have learned how to smell, and it's rather smell than taste or tactile.
They don't see in UV or anything.
Not to my knowledge, or not in any papers that I have read on moose physiology.
Oh, man, I get bread burned.
I'm
Every time I hand
murdered.
it,
All right.
No, this one's from Zoe Tinkle.
Oh,
we have,
hi,
a,
Zoe.
we have a call-in.
Without the predation pressure from wolves, how do you expect the vegetation to respond to the potential increase in browsing frequency?
I expect it to go away. So moose browse on balsam fir within a certain age range. There is a point where the tree gets high enough that it's not going to die from browsing. And then there's a point where it's so small that it's under the snow and the moose can't find it. So in that window is when it's at its most vulnerable. And we had, while we were on the island, we saw trees that were 15 years old that were that tall because they keep getting browsed. They can't get out of that window. And with the wolves going away and the moose population increasing, I expect the population of these browsable trees to dramatically decrease.
Oh, here we go. I
Kevin,
love it.
You mentioned at the beginning about this sort of interactive effect of top-down and bottom-up drivers on moose population density. And then you talked mostly about the bottom-up effects, right, the plant chemistry. I'm curious if your work has elucidated like the relative impact of those two forces on this population, although I understand this one, like the number of predators is quite small. But if you could take what you learned here and extend it to other places, like where and when would you expect the top-down to be most important or the bottom-up to be most?
I would say in ecosystems with abundant food resources that are relatively nutritious, top-down would be the most important. In ecosystems with limited food resources, I would say the bottom-up would be the most important because their susceptibility to top-down controls can be considered through that equation that I showed you a function of bottom-up controls. So if they're not eating healthy food, they're not strong, they're not fit, they can't run as fast or as far, they're more susceptible to predation. So I would say that it's resource dependent on the ecosystem that they're at.
So going off of that, is there any evidence that wolves are selective in what they're eating? And just to frame that, I'm thinking, is it possible that moose or other ungulates are picking toxins that would somehow get wolves to not eat them?
That's a good idea. I like it.
I don't think so. I don't obviously know for sure what the bioramification of the plant toxins in animal protein is, but I don't think that there's a lot of that.
If you shoot like a mule deer that's been eating sage compared to a whitetail that's been in a forest, you can taste the difference. And
Yeah.
Eventually, wolves can smell the difference.
I don't know, Chelsea.
What? Can I ask a question?
Yes.
So, you mentioned that camping is really strongly correlated with another monoterpene.
Mhm.
Is there any monoterpene that they might be like inversely correlated with? So as camping increases, there might be another one that they could be actively selecting against by like choosing camping instead.
I looked for that, and I have the table in my thesis, but not here. There is none. There is no inverse correlations.
So they are actively selecting for camping and not like against some other toxin. Cool. Thank you.
Okay, so you had mentioned that the toxicity might change within the rings of a plant, so the because year to year as they go up. So I was just wondering if you had happened to look at maybe are they choosing specific rings? Like, is there a difference where are they just? Did you find that they were just reaching over and getting what they could get, or maybe they can smell it enough where they're looking at different rings? And I don't know if you did anything like that. Just curious.
Yes-ish. If I can find it. So the very tippy top of the tree right here, this terminal stem seems to be their favorite. They aim for that if they can get to it. And what happens, morphologically speaking, they bite off this stem, the next year the tree grows multiple stems. They have multiple terminal leaders. This seems to be, the brand new growth seems to be their favorite, which makes intuitive sense because it's the newest food. So the top whorls, that seems to be where they like to focus. However, I mentioned earlier that the trees have this range of age that they're susceptible to browsing. And within that range, from the trees we saw when we were on the island, is just, it's a free go. If it's sticking above ground, moose are going after it.
Which one of those whorls are the most toxic?
Yeah, that was my question.
Right.
That would really depend on a lot of things, and I think toxicity is probably not the question. I think the ratio of woody to needles is the question. So in these lower whorls, where to go? Right there. So in these lower whorls, the twigs are thicker. So you have the same amount of needles, but more wood. And in the topper whorls, you have thinner, so you get more nutritious needles, less wood. And I think that is the driving factor rather than the toxins that are in it. Debbie?
All right, last question anyway, but just so that we can move on. But before you ask that question, it's going to be the best one ever, right? The best question. I just sounded like Trump.
Yes.
Sucked. I'm sorry. I know. But just so that everyone knows, so that as soon as when this question's done, come to my house tonight. If you can ask him more questions, and maybe we can talk more about toxins. So
And there's lots of
hit it.
Okay, so you're talking about this window that they can be fed on. Is there fire on the island at all? And if there is, have you ever tracked that across your 18 years of samples?
There is fire on the island. However, it's not as prevalent as it is here. So what I can tell you is that this diagram of the island shows the spatial heterogeneity of the balsam fir. This center right here in the island was subject to a severe burn in 1936, and browsable trees have not fully recovered yet at that point. So we focused most of our sampling on opposite sides of that severe burn area. Fire is a factor in any woody system, but this system, my experience, was incredibly wet. So that's not as big of a factor.
Scary.
Was that a good enough question?
That was great.
It was great.
Okay, thanks,
All right.
Dan.
Thank you for coming, everybody.
Come tonight.